So the next chapter that we are going to cover in this course is queuing models and the simulation applications of the queuing models. Our objective is to provide an introduction to queuing systems and explain the characteristics which will help us to define a queuing system. Then the technical part of this chapter, the second and the third sections, are going to be covered. So in discrete event system simulation, we are basically trying to analyze the behavior of a queuing model. Whatever the system that you are trying to model, we usually use a queuing model to define that system. For example, if you consider a production system, in a production systems, the raw materials arrive and they are either transformed using a production process or they can be assembled. And in the end of the system, the raw materials are transformed into final products or half-finished goods. So here the entities are raw materials. They are coming to the system and requesting a production service from the servers, from the machines, for example, or from the assembly stations. And then they get out of this production system as a half-finished good or a complete product. So if you intend to model such a system with a simulation model, obviously what you are going to model is going to be a queuing system. In repair and maintenance facilities, sometimes a single, sometimes multiple machines break down at the same time, and the maintenance servers, the maintenance crews, they are going to repair these machines in a order based on a policy. The order of the repair service must be based on a repair policies. And again, the machines that are asking for a repair service are getting into a queue to take a service from one or multiple servers. Communication and computer systems are also queuing systems where people intend to send a message. They are basically getting into the queue of a server, and the processors are processing these messages to direct them to the locations they are sent to. Or if you consider a transportation service like public transportation, I mean, even by simple thinking, you see that you are going in a bus stop and getting in a queue there. So you are waiting for the bus that you are looking for to come to the station and take you. In a material handling system where we handle the materials within the production facilities or from the production processes to the transportation devices, again, the products which are going to be transferred or handled are getting in a queue, and the servers here are the material handling devices like forklifts or conveyor belts, etc. And in service industry, service facilities, again, either it's a financial facility like bank or a dining facility like a restaurant or an education facility like a school or a health facility like a hospital, people are getting into queue to get a service. So you see, whatever system you are trying to model here, in most of the cases, we are getting involved with a queuing system. And queuing models are analyzed and solved for measuring the performance of such systems. So what do we measure in a queuing system? For example, the server utilization. Imagine a simple hairdresser shop where two hairdressers are working, and we may be interested in the percentage of time where the servers, which means the hairdressers, are being utilized. So sometimes they are going to remain idle because there is no customer to server. Sometimes they will be busy because there are people getting a service and there are people waiting in the queue. And the server utilization is a good performance measure. We would like to have the utilization of servers as large as possible. But not in every queue, the server utilization is at 100%. Similarly, the length of the waiting queues is also another important measure, because if you are a customer coming to a hairdresser shop and if you see there are too many people waiting in the line or waiting in the queue, then you would prefer to go somewhere else, not to this hairdresser shop. And because of that reason, length of waiting lines, or at least the average length of the queues, is an important performance measure. While we expect the server utilization to be high, we also would like to have the length of the queues small so we can attract more and more customers. And delays are also other performance measures. We would like these delays to be as small as possible because the delays, they can be seen as a waste. The delays do not contribute anything to the service or the transformation of the entity. It does not contribute any value to the whole process. So we would like these delays to be minimized. However, as a result of the queuing policy or the service policy that you have defined, these delays or the length of waiting lines or the utilization rates, we see some undesirable conclusions about each of these performance metrics. And by optimizing the queuing policy or the service policy, we would like to optimize these performance metrics as well. And queuing models are going to be very helpful for us to optimize such performance metrics by changing our service policies. Now, the system performance in a queuing system is a function of the input parameters. For example, the system performance is dependent on the arrival frequency of the entities. Let's just imagine a simple queue. There is a hairdresser shop where we have a single hairdresser and the people are getting this hairdresser shop to get service. The arrival rate, the average number of entities or people coming into that hairdresser shop, is an input parameter which affects to the system performance. The service demands of the entities is also another input parameter. So if we are going to model such a queuing system, first we need to model the arrival process of the entities, for example, the distribution of the inter-arrival times, and the service demands. So which customer is coming to get a haircut and which customer is coming to get a shave, or there are several services that you can get from a hairdresser shop. So depending on the service demands of the entities, the service times can be affected. And similar to that, there is also a service rate or a service speed to that specific service. Not every haircut process is going to have the same speed, right? It depends on the type of the hair and the model that the customer is requiring. And sometimes we may have multiple servers in a queuing system. For example, the cashier queues in a supermarket, we may have one or multiple parallel servers. So you get in the queue, which is the shortest usually. So the number of servers is another input parameter which you can define and which affects the system performance. Now, you definitely have a control on the number of servers as a manager, right? You can change this. However, it is almost impossible to change the arrival rate of the entities. I mean, you can offer promotions to increase the arrival rate maybe, but you do not have a 100% control on the arrival rate. However, the number of servers you can change. Arrangement of servers is also another important input parameter. We are going to see the distinction between serial servers and parallel servers. Some servers can stay parallel and you can get your service from any of the servers that you choose. However, sometimes the servers can be serial. For example, you need to go through server 1. Then after finishing your task in server 1, you need to go through server 2. So this is called a serial server policy. And we can explain the service policy by a very, very detailed explanation. There are different service policies which we are going to cover. These are sometimes under the direct control of the service policy maker, sometimes partially, and sometimes you do not have any control over these input parameters. So either you have a control or not, it doesn't matter. We definitely need to find a model for these input parameters, and then we can use a simulation model to measure the system performance of a queuing system under a certain service policy. Now, for relatively simple queuing systems, the performance measures can be computed mathematically. So queuing theory is a very, very old discipline in mathematics. And in that discipline, some scientists have developed formulas which can exactly calculate the performance measures. However, these simple queuing systems are unrealistic. So practically, we do not observe such simple queuing systems for which we have closed form performance measure formulations. However, why do people study these simple queuing systems? Because these simple queuing systems, they help to understand the dynamic behavior of queuing systems. Even the description of the queue is very simple. You will see that the behavior of the queue, the dynamics are changing incredibly if you change the policy. So we study these simple queuing systems, so we see how they can change their dynamic behavior based on input parameters. And from here, what we try to understand is the relationship between input parameters and the performance measures. So changing an input parameter, how does that affect the performance measures? So we can understand these relationships in simple queuing systems to understand this effect on complex queuing systems as well. However, for realistic and complex queuing systems, mathematical formulations for performance metrics are usually not available, and usually simulation would be the only option to measure the performance metrics of such complicated queuing systems.